In this lecture, we are going to learn another kind of product between two vectors. This is called the cross product instead of the dot product. In order to compute the cross product, first I need to tell you what determinants are. Determinant actually is a short way of writing a long, sort of operation. So we write a determinant of order 2, which means 2 rows, 2 columns. It's like an absolute value of these 4 numbers, A, B, C, D. But it's not absolute value. It could be positive or negative, okay? But what you are getting is a quick way of putting this complex operation together. Is AD minus BC. So for example, I have this determinant 3, negative 2, negative 1, 2. Then it is 3 times 2 minus the other diagonal, negative 2, negative 1. So this is 6, take away 2, which is 4. Now, when we have an order 3 determinant, which is 3, we call it 3 by 3. Because it's 3 rows and 3 columns. Then what you do is use here, what the definition I have here, we expand it from the first row. Okay, so each time you take one element in the first row and then you cross out its row and its column. Whatever is left will be a 2 by 2 determinant, and that will be what goes following A1, well, the first number. Then you start over with the second number, A2. Then you cross out the row and the column that A2 is in. You have B1, C1, B3, C3. Finally, we have the third element in our first row, and then same thing, we cross out the row, we cross out the column, and you are having B1, B2, C1, C2. Notice that the sign of these products alternates. When you are expanding by the first row, which we are only going to expand the determinant by the first row, although actually you can choose any row or any column to do it, but no, I'm not going to get into this. So when we are expanding from the first row, it starts with positive. That's why when it's 2 terms, it's positive, then negative. When it's 3 terms, it will be positive, negative, then positive. Okay, so if you are going to compute the determinant of order 4, which we are not going to, it will be positive, negative, positive, negative. And what is left will be degree 3 determinants. Then you keep sort of making them smaller, compute them. But again, we're not going to get to order 4. Order 3 is what we really need. Okay, so here again, I have this determinant for you, 3 by 3, 3 rows, 3 columns. To compute it, first you take the first number, and then you take away its row, you take away its column, okay? That's why we are having 1 times this corner, 0, 4, 2, 4. I like to copy the things by column because you are taking away the first row, so you are looking at the second and the third row anyway. So you are reading, sort of copying downward. That's why I prefer to copy the whole second column. Well, not whole, but the 0 and 4, then the 2 and 4. I don't like to do it horizontally. But if you prefer the other way around, I don't mind. And the reason I don't like to do that is the following. Now, I'm getting to my second term, which I'll cross them out. See, if I do 3, 2, negative 5, 4, I sort of have to jump twice. But if I do 3, negative 5, 2, 4, I only need to jump once. And that's really the reason I like to do them vertically. So this is the second term. Remember, you need to minus the 2, then 3, negative 5, 2, 4. Finally, you are at the third. We are plussing, but it's a negative 2. Then we take away them. And we're getting 3, negative 5, 0, 4. Each of these is a 2 by 2, right? Determinant, which you need to compute with the definition up here. So it's 1 times 0 times 4, 0, take away 2 times 4, 8, minus, oops, where did I get that from? Okay. So 0 minus 8, minus 2, 3 times 4, 12, take away 2 times negative 5, negative 10, then plus negative 2, 3 times 4, 12, 0 times negative 5, 0. Okay, so each of them is 1 times negative 8 minus 2 times 22 plus negative 2 times 12. So I'm getting negative 8 minus 44 minus 24, and that gives me, well, they're all negative. So 8 plus 44, 52 plus 24, 76, and negative. Okay, that's how we compute a determinant of order 3. Now you can try your practice. Number 1, same thing, compute a determinant. Now, since you know the determinant, we can talk about the cross product. The cross product is, well, first of all, what is the cross product? You have two vectors in R3, okay, which are A and B. So the A is this way, the B is this way. Again, we are using the right hand rule. You put your right hand here, okay, goes from A to B. Your forefinger, okay, this is goes from A to B. By going from A to B, I mean go from A to B with an angle that is less than 180 degrees. Okay, so you go there, then the thumb will point at somewhere, but that somewhere will be the direction of A cross B. So the most important or the most obvious example is when you do X, Y. If you do X and Y, you get the Z, right? Direction of Z. So when you put your X-axis and Y-axis and you want to know where the perpendicular direction is, so that's what your right hand rule give you. So in general, if your X and Y are not perpendicular to each other, the two vectors are not perpendicular to each other, you still can do that. The right hand rule will give you somewhere, a perpendicular vector. And that is what we're looking for. And later I'm going to tell you what it really, well, that's the direction, right? And its length also means something. But for now, let's do the computation first. We define the cross product of A and B, which are the general form, A in R3 and B in R3, both vectors. Then the cross product will be again a vector since it has direction, right? So each of them is A2B3 minus A3B2. Then the second coordinate A3B1 minus A1B3. Then the third coordinate A1B2 minus A2B1. What are they actually? If you put them in the determinant with the direction, the basis of our vector space, ijk on the top row, that's my A2B3 minus A3B2. And this is the A1B3 minus A3B1, but negative. You're in the second term, you're supposed to have negation. And finally, here you have the a1, b2 minus a2, b1. So when you are putting your basis on top, and you have a vector A on the second row, and you have vector B on the third row, you have a determinant. And when you compute it, I, j, and k, which are not numbers, so at the end you will end up with number times vector I, number times j, number times k, and that is your new vector. So here, example, I gave you the A and the B. We're going to find the cross product. So the A, vector A cross product B equals my determinant with I, j, k on the top, then A on the second, 2, 1, negative 2. The 2, the 1, the negative 2. Okay, you take the coefficients. Or you can think this is 2, 1, negative 2, and B is 3, 2, 1. Right? 3, 2, 1. That's your B on the third row. Then it equals, I fix my I, but since I, j, and k, you are not going to really multiply them, you can leave them at the end instead of the beginning. If you want to put them in the beginning, I don't mind. But personally, it's like coefficient, then the variable. That's why I prefer to put I later. So I have the 1, well, here, you take that away. 1, 2, negative 1, 1. Okay, then my vector I. Then you're up to j, that's negative. Then you take away the j column and j row, you have 2, 3, negative 1, 2. 2, 3, negative 1. Sorry, negative 2, 1. That's what I meant. J. Then plus, you take away the k, you have the lower left corner. So we are having 2, 3, 1, 2, k. Now compute. This is 1, take away negative 4, I, minus 2 minus negative 6, j, plus 4 minus 3, k. And that gives me 5i minus 8j plus 1k, or just k. And that's the vector A cross B. Now you can try practice number 2. Some remarks on our new thing, the cross product. First, unlike your inner product, the dot product, you can define on any vector space. The cross product only works for degree 3. Okay, it's a unique thing for 3-dimensional vector. And as we already point out, the cross product is a vector. Remember, the dot product is a number, but the cross product is a vector. And with the practice, hopefully you see that when you switch the two vectors, A cross B and B cross A, are two different things. So the product of the cross product of A and B and A are different. Okay, you cannot switch. You don't have commutative law in cross product. You do have commutative law with the dot product, not here. Also, you don't have commutative law with you don't have associative law with the cross product either. So not commutative, not associative. Okay, you don't have those laws. Finally, getting from the right hand row, the new vector that you get is perpendicular to the plane that has A and B. So it is actually perpendicular to both A and B. For example, what we just did was A equals the 2, 1, negative 2, and B is 3, 2, 1. Although in the example 1, when I gave it to you, it was in the basis form, not just the angle bracket form. But same thing, and we got A cross B equals 5, -8, and 1. If you do the dot product, 5, -8, and 1, dot product 2, 1, -2. Remember how you do it? You do 5 times 2 plus -8 times 1 plus 1 times -2. You get 10 minus 8 minus 2, which is 0. Which means cosine theta equals 0. Or theta equals 90 degrees. But what are you computing? You are computing the angle between the cross product A cross B and the original vector started with A. So the new vector A cross B is perpendicular to A. Similarly, you can verify B as well. Keep going. If theta is the angle between A and B, actually the length of the cross product is A, the length of A times the length of B times sine theta. So when you are having the B sine theta, actually B sine theta is the height in this parallelogram that formed by vector A and B. Okay, so that's where we got the following two corollary, which is, you have a theorem. Then immediately you get some important but easy result from theorem. You don't need to do a lot of work to show they are true. That's corollary. So first, if sine theta equals 0, if the cross product equals 0, then sine theta equals 0. Sine theta equals 0, the theta equals 0 or 180 degrees. Okay, so if you didn't start with a 0 vector, but you end up with 1, that means the two vectors are parallel. Or parallel meaning they go to the same direction or opposite direction. Also, the length, the magnitude of the cross product is the area of the parallelogram in this graph. Okay, so the cross product has its angle. The direction is the direction that perpendicular to both vectors you start with, and the length of the cross product vector is the area of the parallelogram that the two vectors forms. Okay, that's the length and the direction. Now example 2, given these 3 points, we want to find the vector that is perpendicular to the plane of PQR. Okay, so that's another way of saying, PQR. There are 3 points. So no matter what you do, you pick a point to start. You are going to form two vectors. I'm not saying they are in the same plane on XY, but it will be a plane because you have 3 points that determine a unique plane unless they're on the same line. So when you have these 3 points, you can find the plane, and then you can find the direction that is perpendicular to it. How do you find it? That would be exactly the direction of the A cross B. If you call this A, this is B, then this will be A cross B. Sorry, the other way around. Mine is B cross A. So what you need to do is you just need to find the two vectors. Actually, it doesn't really matter. You can do it here, P, Q, R. You can choose start with Q and do it here. They will all be parallel. but I'll choose P to be like the base point since it's the first one. So the vector that starts with P goes to Q will be the terminal point minus the initial point, coordinate by coordinate, 4 minus 3, then negative 1 minus, negative 2. That is negative 2, 1, and 1. Then my second vector, which is PR, is 2 minus 0, 1 minus 3, then negative 1 minus negative 2, which is 2, negative 2, and 1. Then I can do the cross product. PQ times PR cross is IJK. Then my PQ, negative 2, 1, 1. Then my PR, 2, negative 2, 1. And that is 1, negative 2, 1, 1 for I minus negative 2, 2, 1, 1 for J. And I don't have room. Oh, I should have take away that. So I'll do it here. Plus the K part, negative 2, 2, 1, negative 2, K. And let me take that away. This equals 1 minus negative 2. That's 3I minus negative 2 minus 2, negative 4J plus 4 minus 2, 2K. Or 3I plus 4J plus 2K. Now the area of triangle PQR. So here's my P, here's my R, here's my Q. The triangle is this. And we know that the length or the magnitude of our cross product is the area of the parallelogram of the two vectors putting together A and B. So essentially, we are getting the parallelogram by taking the absolute value. Then our triangle actually is just half area of the whole parallelogram. Right? This is your parallelogram, and when you connect, sorry, that's too bad. So P, we are doing P, Q, and R. I connect my Q and R. I cut my parallelogram into two identical triangles. So the area of the triangle is half area of the parallelogram. And we know that the area of the parallelogram is the square root is the is the absolute value or the length of our cross product. So it's 3 squared plus 4 squared plus 2 squared, which is square root of 9 plus 16 plus 4, that's square root of 29. Then the area of the triangle will be half times square root of 29. Or square root of 29 over 2. That is the area of the triangle. Now, triple product. When we have a cross product, it's a vector. When we are having a dot product, you get a number. When you have 3 vectors, you can do cross product, 2 of them, and the dot product, the third one. Okay, actually, when you have A, B, C, you put cross as some, so pretty much you are having A, B, and C, you put cross between 2 of them, then you dot the third one. Cross goes before dot anyway, because you need, it comes out as a vector. Okay, so we have the associative, well, not really associative law. So it doesn't really matter which 2 you pair together when you have A, B, C together, but you have to do it in order. Then what happens is you do A dot product B cross C, or A cross B, then dot product C, and then they're the same. And actually, we have commutative law for the dot product. You can also switch it, more than just these two versions, but I'll leave it here. Because actually, it doesn't matter, you will end up with the same thing. It is the determinant of order 3, and the 3 rows are vector A, vector B, vector C. Well, I'm not going to really make you to do this. Oh, well, by the way, this is called the scalar triple product. Okay, I'm not going to really make you to do the cross and then the dot product. Instead, what we are getting is the volume of the parallelepiped. So coming out from one endpoint as the common initial point, you have 3 vectors coming out, A, B, and C. And then when you make first like a base, you use 2 of them to make a parallelogram, and then you also grow along the vector of A upward, and then you have the matching top. That's the parallelepiped. And when you do this scalar triple product, or rather when you do the determinant of the 3 vectors A, B, and C together, you are getting, well, by the way, this number could be positive or negative. When you take the absolute value of it, you are going to get the volume. This is a 3-dimensional thing. So you are going to get the volume of the parallelepiped. And notice that when you are having the dot product, this is a number. And when you, I type one more than necessary. And then when you take absolute value of the number, you are getting its volume, which is positive. Now let's see. Example 3. Find the volume of the parallelepiped determined by 1, 2, 3, negative 1, 1, 2, and 2, 1, 4. So pretty much all you need to do is to just put the 3 vectors in your determinant. Negative 1, 1, 2, and 2, 1, 4. And then this is 1 times 1, 1, 2, 4, minus 2, negative 1, 2, 2, 4, plus 3, negative 1, 2, 1, 1. Then it's 1 times 4 minus 2 is 2, minus 2 times negative 4 minus 4, negative 8, plus 3 times negative 1 minus 2, negative 3. So that gives me 2 plus 16 minus 9, which is 18 minus 9, 9. Okay, then the volume is, well, you already have positive, so it doesn't really matter. But in general, when you are having the number which could be negative, you take the absolute value. What am I saying? You take the absolute value of the number which remains positive. That is the volume of this parallelepiped. Again, there are a lot of properties I can't really cover in my lecture, but I want you to be aware of them. A lot of nice things happens with our cross product. Cross product is not commutative, but when you commute, you get a negative sign. When you switch the 2 vectors, you get a negative sign. Then you do sort of have the scalar associative rule, which means you multiply a scale, a multiplier number C on any of the vector, we multiply it at the result of the vector is the same. Okay, and we also have distributive law. So it's a product. So when you do the product with the sum, it's the same as the sum of the products. Those are true. And in particular, I want to draw your attention to these rules. These are the rules on the basis, which is if you are doing the cross product of ijk in order. Okay, so you get ij. You start from ij, you get k. You are doing a loop, I, j, k. Then you go back to I. If you are you are following this order, you just get the next vector. Jk give you I, ij give you k, ki give you j. But if you are going backward, ji, since you are going backward, you are going to get a negative sign. Okay, so if you go this way, it will. This is I don't know how to make it work. So when you go this way, I cross k, that's what I'm saying. You are going backward, will give you negative I. Okay, because you are not following the order of this loop. ijk, ijk, ijk. You are doing kji, 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 then it's okay. J cross I give you the previous, which is k. But since you are going against the order, you are getting a negative one. So j cross I give you negative k, k cross j give you negative I, and which one am I missing? I cross k give you negative j. Okay, it's again very easy to verify if you put them in the cross product definition, but if you know some tricks, you don't have to do it. And yeah, that's it for this lecture. Now you can try the practice number 3 through number 5.